Good afternoon, informs, presenters, and attendees. My name is Badri, and I work at Rajulakshmi School of Business as Associate Professor in Business Analytics. I thank the Chair of Inform's Petrochemical Cluster, Dimitri Papa George, for inviting me to speak at this session. I also thank Pablo Garcia Herrero from one of the largest copper producers, Oribis, for chairing this session. I'm presenting recently published work on logistics management at Indian Oil Corporation. My co-author is Atanu Sanyal, who's Chief General Manager at Haldia Refinery in Indian Oil Corporation. Um, he shared all the industry data that was used in this project. I made a spreadsheet model and used a solver and did the sensitivity analysis and so forth. So first of all, I would like to show you the part of the transshipment network that we focused on. So this is the northwest corner of the country, and on the left you can see the production sites in yellow. In the middle are the two ports that are used for uh, receiving the supply and shipping it further to the refineries. And on the right we have three refineries. The company has many more refineries all over the country, but we are focusing only on this region. Okay, so here is the mini network, and you can see we have four production sites. The H over here is for high sulfur crude, and the L in the node represents the low sulfur crude. So we have three suppliers of low sulfur crude and one supplier of high sulfur crude. The Persian Gulf supply, is 15 million metric tons per annum. West African supply is 17 million metric tons per annum. North African and West Asian supply is 2 million metric tons per annum. And indigenous supply from India is 2 million metric tons per annum. USA is now supplying 1 million metric ton per annum, but it's not included in this uh, study because it is a recent development. The two ports in focus are Vadinar and Mundra. I will show them on the company map. Then the three refineries, Koyali, Mathura and Panipat. And you can see the refinery capacity for this refinery is 15 million metric tons per annum, out of which half of it is good for sour crude. Mathura refinery, which is further north, uh, has a capacity of 9 million metric tons per annum, and 5.4 million metric tons per annum is good for sour refining. And finally, Panipat refinery has a refining capacity of 15 million metric tons per annum, and the sour refining capacity is 13.5 million metric tons per annum, which is almost 90%. Then over here in between the ports and the refineries, we have a pipeline which is 30 million metric tons per annum capacity. It's good for both types of crude. There's also a railway line from existing from before, and on from this port to Panipat refinery, we have a lower capacity pipeline which is 9 million metric tons per annum, and this is a dedicated pipeline for high sulfur crude, so you cannot transport the low sulfur on this pipeline. So this is the position. Um, One word about the transportation options. We have VLCCs, which are very large crude carriers, which go around Africa and take a longer time. Those are uh, available for Persian Gulf and West Africa. Then we have Suez Max vessels that can go through Suez Canal, and they are available for three of the four supplies. And we have long range vessels which are for regional transportation. So I'll tell you about the capacities of these vessels soon. Now this is the company map, um, and you can see the two ports are over here, Mundra and Salia, and this is called the Gulf of Kutch. And then these two black lines going up northeast direction, uh, one branches off to this refinery, Koyali, which I showed you on the network. Then the pipeline goes up and one branches off here to Mathura, and then it continues to Panipat. So both of them continue to Panipat over here. So these are the three refineries, these black structures. Now some engineering terms that everyone needs to know about this industry is 1 metric ton equals about 7.3 barrels of oil. Uh, Furthermore, about 95% of a barrel is used and converted to refined products, leaving only 5% as residue, coke residue. Then crude oil with sulfur content more than 0.5% is referred to as sour crude oil. So there are some elements which are considered impurities, and the crude oil is considered sour. If those elements are not present, the crude oil is referred to as sweet. And the gross refinery margin is $8 per barrel for the superior crude and $6.5 per barrel for the sour crude. Now, the crude basket. So the purchasing choices are many. The benchmark prices are Brent from North Sea region. So Norway, North Sea oil is one benchmark. West Texas Intermediate is for the American crude. And in the Arabian Gulf, we have the Dubai benchmark price. And there are a lot of other prices which I'm not getting into. The supply I've shown you on the network. Now the vessel capacities, the VLCC has a capacity of 270,000 metric tons or 2 million barrels. The Suez Max has half the capacity of the VLCC, and the long range vessel has a capacity of 60,000 metric tons. Now the cost of these vessels, VLCC from Persian Gulf costs $2 million per voyage. This includes all the inventory cost and holding cost per day. Suez Max from Persian Gulf costs $1.5 million per voyage. VLCC from West Africa costs $3.5 million per voyage. And Suez Max from North Africa and West Asia costs $2 million per voyage. And the long range vessel from Bombay High costs $0.4 million per voyage. Pipeline type and capacity. The SMPL pipeline is 2,660 kilometers long and has 30 million metric tons per annum capacity, as I mentioned, and it runs to all three refineries. The other pipeline is 1,194 kilometers long. It has 9 million metric tons per annum capacity and is dedicated to transporting sour crude oil. Next, I'll tell you about the mathematical model. We had an objective function which was a maximization type for maximizing gross refinery margin, and we subtracted the costs, which were the transportation costs, the inventory costs, and the pipeline costs. The constraints were supply constraints, the transshipment or node balance constraints, which are there in the network, refining capacity constraints, because we have a capacity for sour crude refining and total refining capacity. Then flow conservation constraints. Since we are dealing with parcels of low sulfur and high sulfur crude, we have to keep track of all those parcels and make sure they uh, tally. Then we have blending constraints. How do you combine the two crudes to get the refined products? Now, I'll show you the spreadsheet model that I developed. So here is the spreadsheet. You can see the cost coefficients on the first row, then the variable names, and then in the third row in this red bordered cells, we have the target cells. Then we have the objective function over here. And then we have a block of constraints. And you can see which variables are integer. And for example, these are the supply constraints. And then we have the transshipment constraints, and this yellow band over here is the blending constraints. So I ran the solver and got the solution, and next I would like to show you the solution. So we got a product mix of 19,579.5 thousand metric tons of high-grade gasoline and 14,235.75 tons of low-grade gasoline. The maximum gross profit was almost $9 billion. Now, that's a healthy profit, and but the utility of this model is we can tell the shipping pattern almost exactly. We have 23 and 32 VLCCs required from Persian Gulf to the two ports. Similarly, from West Africa, we require 62 VLCCs to Wadinar and none to Mundra. So the total number of VLCCs required is 170. Now, similarly for Suezmax vessels, we can tell how many we require. And we also know how much of low sulfur goes to each port and how much of high sulfur is shipped to each port. Now on this slide, I have indicated all the solution numbers. So 22, 32, these are the requirements. Then on the pipelines, you can see how much low sulfur is transported and how much high sulfur is transported. And finally, the utilization. You can see this refinery is utilized only 80% because all the high sulfur crude is shipped further down, and the two refineries which are upstream are, downstream are utilized almost 100%. So here are the pipeline flows. Now, sensitivity analysis, before I wind up my talk, you can see we varied the gross refinery margin across a range of numbers, and these colored cells indicate that the solution is quite stable for a range of price coefficients, and these columns also show that changing the price coefficient for the second product doesn't affect the solution unless you make it very low. So only if the price drops to 2,000, 20,000 or 30,000 does the product mix change, otherwise it's quite stable. Here are two charts which show that the product mix stabilizes at these two values. So in conclusion, what is the useful features of this model? You can scale it up to more, uh, uh, more suppliers, ports, and refineries. And second, it tells you exactly how many ships you require to do the transportation. It reveals imbalances in port utilization due to development or expansion or new technology. Now, here are some additional slides on sensitivity analysis. So some changes in right-hand side coefficients affect the solution. Some changes don't affect the solution. As you can see, changing the refining capacity at Coeli doesn't affect the product mix at all because there is some, it's not a binding constraint. So in conclusion, the solution we obtained is quite stable given the sensitivity analysis to coefficients, and we can understand the refining capacity utilization to this model, and we can expand it to new suppliers, ports, and freight options. This paper has been published in uh, a top French OR journal, Rado Operations Research, only this year, and copies are available for free at their website. So if you want to see the equations, you can download this paper from the website. Finally, I would like to thank many people who helped me uh, develop the model, do the analysis, and publish the results. Finally, thank you for your time, and hope you have a productive year until the next annual meeting.